That number is not something we encounter normally, so we need a way to understand it, to be able to intuitively recognize what it means. So how can we understand how small this number is? 10 to the minus 5 billionth is a decimal followed by 4,999,999,999 zeros followed by 1. So we can try and write this out. So we'll start with this batch of zeros. Here's another batch of zeros. We add more zeros. We add more zeros. And we need another 10,822,510 pages, just like this field with zeros. We're going to skip that. Then we wind up with this at the end, which is 10,822,510 pages of zeros. So this is a small number, but it isn't clear how to understand it, how to interpret it in reality. So this is not helpful writing it out. We need a more intuitive way to understand this small number. To do that, we first need to look at how we can evaluate scientific theories. I'd like to suggest there are at least 3 questions to ask about a scientific theory. The first question, is the theory possible? And to be possible, it must be logically coherent and grounded or based in reality. For example, a married bachelor is not logically coherent. It's a contradiction. In the picture on the right, you see a lady balancing on top of 3 balloons, and the bottom balloon is below the bottom balloon is a nail. That can't happen in reality because the weight of the girl would force that bottom balloon to pop. The second question, is it plausible? And plausibility follows from possibility. So the first question, is it possible? Then you ask, is it plausible? By plausible, we mean it fits all the facts and passes the nonsense detector. Or it fits most of the facts and passes the nonsense detector. And there can be several theories that are plausible. It doesn't mean just one. And then the next step is to look at the plausible theories and ask, is it probable? The one we would select would be the best explanation for the data, and it must be more likely than all the alternatives. So you have three questions to evaluate a scientific theory. Is it possible, is it plausible, and is it probable? For example, if we were to talk about possible theories, we would look at theoretical physics. If you look at theoretical physics, it's math, and they build models. And those models could be real, but they may have models that don't match reality too. So is it plausible we introduce facts about reality, and we exercise the nonsense detector? So that's where we're focusing today. We're asking, is undirected macroevolution plausible? Does it fit all the facts, and does it pass the nonsense detector? So let's take the next step to make this really understandable. When we try to understand something, we compare it against another thing. So we need a measuring stick to compare against. We want that measuring stick to be as simple as picking a green ball from a bag of colored balls. And we make other comparisons using our measuring stick. For example, we have a blue measuring stick and a green measuring stick. If we look at the green ruler in comparison to the blue ruler, we see the blue ruler is about 3/4 of the height of the green ruler. So we can make that comparison. Then we check if those comparisons fail the nonsense detector. And this may seem a little abstract. We'll make it very concrete in a minute. We're going to use a paper as a template. The paper was written by David Abel. It's called the Universal Plausibility Metric and Principle. It was published in Theoretical Biology and Medical Modeling in 2009. Excellent paper. Suggest everybody read that paper. He introduced something called the universal plausibility metric. We're going to not refer to that term. I just wanted to bring that up. So we would want to, we start by answering what is the largest meaningful number in the universe? Well, we want to include all matter, which is everything. And that's 10 to the 80 protons, neutrons, electrons. Now, I don't want you to get too hung up on the precision or accuracy of these numbers. If these numbers are out by a factor of a billion, it doesn't really impact the result. That's what you'll see. So let's just go with 10 to the 80 protons, neutrons, electrons. What is the fastest rate possible? What is the fastest rate of change? We're going to look at a number that's faster than any chemical reaction, and that is something called Planck time. It's the smallest meaningful unit of time. And that can be 10 to the 43 changes per second. Then we're going to include the maximum amount of time possible. Let's say the universe is between 10 and 20 billion years old. Let's just round up to 10 to the 17 seconds. So if we take the biggest numbers in the universe, all matter, fastest rate possible, maximum amount of time, we come up with the largest number of possible events in our universe, which is 10 to the 140th power. What that's doing is it's taking all matter, changing at the fastest rate for all time. So if we call each change an event, then there can be 10 to the 140 events in the entire lifetime of our universe. I want to point out there is no larger meaningful number in the physical universe. Now, I know somebody's going to quibble and say, oh, what about this thing over here because it is a much larger number. My criteria is something that is observable, something that is real, not something that is theoretical. And again, if we're off by a billion or a billion billion or a billion billion trillion, it doesn't matter. The results will be the same. Now, if we say that the largest number of things we can identify in our physical universe is 10 to the 140, then selecting just one of those gives us the smallest probability. And that smallest probability is selecting a specific event from all possible events in our universe. Remember, we want this to be as simple as picking a green ball from a bag of colored balls, and that's what we're doing. We're going to, if we were to take an event of a transition that happened at Planck time rate and mark it with an X, and then we had the opportunity to select any event from any atom throughout all time, picking that one event out of all of those possibilities gives us our probability. So there is no smaller probability that's meaningful in our universe than the smallest probability our universe can measure is 10 to the negative 140. There is no smaller probability in our physical universe. Let's contrast our smallest meaningful probability in the universe, which is 10 to the minus 140, with the probability of a simple cell forming, which is 10 to the minus 5 billion. Doing some simple math, you would find that we need 35,714,285 universes to have the same probability of the first cell's energy needs being met. Again, you need 35,714,285 universes for the same probability of the first cell's energy to be met. So we're comparing the smallest meaningful probability in the universe with the probability of simple cell forming. You need 35 million universes. How many universes do we have? We only have one universe. So this fails the nonsense detector test. Anything that requires more than one universe is just nonsense. Let's make another comparison with the Powerball lottery. In the Powerball lottery, you pick 5 numbers from the numbers 1 to 69, and you pick an additional number between 1 to 26. Winning has a probability of 3.4 times 10 to the minus 9. How many Powerball wins is equivalent to the 10 to the minus 5 billion? Well, doing some math, you must win the Powerball 42 quadrillion, 328 trillion, 500 billion times in a row. So it's not just randomly winning, you have to win it consecutively. If there was a Powerball draw every second, you would need to consecutively win for 1.34 billion years to come up with an equivalent probability. So you're basically winning the Powerball every second for 1.3 billion years. Yet that would be considered a verified natural law. This obviously fails the nonsense detector test.